Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today, we're going to devote the entire hour to astronomy. In fact, we're going to welcome the new year, 2011, by talking about some of the frontier questions about the universe. Specifically, what kinds of hazards does the Earth face? Specifically, we're going to be talking first about meteors and comets. Our special guest is astronomer Ken Croswell of Berkeley. He's the author of a number of delightful books on astronomy, including Magnificent Mars, The Magnificent Universe, 10 Worlds That Circle the Sun, and also The Universe at Midnight. Well, we're going to be talking not just about meteors and comets, but also about the sun. The sun is our nearest stellar neighbor, and perhaps one day it will die. But before then, perhaps hazards face the planet Earth. So we're also going to be talking about the life history of stars, our sun, as well as stars in the heavens. And once again, our special guest will be Ken Croswell, astronomer at Berkeley. And before we begin, let me make an announcement, and that is if you watch the Science Channel, you can probably catch reruns of Sci-Fi Science, Physics of the Impossible, based on my New York Times bestseller, Physics of the Impossible. Everything you wanted to know about ray guns, time travel, force fields, phasers, teleportation, warp drives, starships, antimatter engines, everything you've ever wondered about from the world of science fiction explained on Sci-Fi Science on the Science Channel. In fact, so far, believe it or not, we have taped 24 episodes. That's right, 24 episodes concerning a wide range of topics that are at the frontier, the cutting edge of our understanding of the universe. So once again, we're going to bring on Ken Croswell, astronomer at Berkeley. And now I'd like to bring on our special guest for today. We're very delighted to have with us once again astronomer Ken Croswell of Berkeley. He's the author of a number of delightful books about astronomy, including 10 Worlds, Planet Quest, The Universe at Midnight, Magnificent Mars. And today we're going to talk about the recent study that NASA simply doesn't have the bucks to scan out of space to look for dangerous comets or meteors. And the question is, what happens if one of them actually hits the Earth? Who's tracking these dangerous objects out there in outer space? And then we'll talk about the latest developments in astronomy. New extrasolar planets being discovered. New discoveries about galactic physics. So once again, our special guest today is Ken Croswell, astronomer of Berkeley, author of a number of delightful books on astronomy. And today we're going to talk about what's out there in outer space and who's protecting us. Ken, it was over the wire services, the fact that the United States Congress has caught NASA in a catch-22 situation. In 2005, Congress mandated that by law, NASA should track 90% of all the potentially dangerous asteroids and comets out there, perhaps 20,000, according to the latest estimate. But then the National Academy of Sciences just this week announced that, well, NASA is out of cash, that it doesn't have the money to begin tracking these things, that no way can it meet the mandated deadline of 2020 to track 90% of dangerous asteroids and comets. So do you think that is kind of short-sighted and unwise to cut back on funding of an incident which might destroy life on Earth?
Well, I think it would be prudent to do a thorough survey to find out everything that's on essentially Earth-damaging orbit. Most of the asteroids that exist in our solar system are between the orbits of Mars and Jupiter. They're not going to do us any harm. But every now and then, one of them crosses the Earth's orbit, and potentially one of those could someday hit the Earth. The problem is we don't know about most of the things out there that exist. And so, if we know about things that exist, if in a perfect perfect world, we would know about everything that exists that crosses the Earth's orbit. We could then see if any of those will someday hit the Earth, maybe 20, 30, 40 years from now. And if we have that sort of advanced warning, then we can develop some sort of mission to, maybe nudge the asteroid away, maybe even blow it up if that turns out to be the best thing to do. But if we don't even know about it, it's a little bit discouraging. You may have heard last October, astronomers did discover an asteroid, and then 19 hours later, it hit the Earth. Now, fortunately, this was a very small asteroid, just about 10 feet across. But, there are things out there that we don't know about that potentially can harm the Earth. So it would be prudent to just do a thorough inventory of the near-Earth space.
Now, anyone who watches the movies believes that there are all sorts of tracking stations, professional astronomers combing the skies, looking for dangerous comets or meteors. However, isn't the reality that most of the searchers are, in fact, amateurs? Total amateurs who are unpaid, who do the thankless job of hauling out their telescope in the middle of the night when it's cold, taking photographs of the night sky and comparing the photographs with the previous day's photographs. So isn't it true that most of the bulk of this work is done by amateurs?
Well, some is done by professionals and some is done by amateurs. We recently had a dramatic case of an amateur making a wonderful discovery of a comet or an asteroid hitting Jupiter. That occurred in the month of July, and he was observing Jupiter, and he noticed this dark spot where there had not been a dark spot before, and that was discovered by an amateur astronomer in Australia, Anthony Wesley. So, yes, certainly amateurs make very important contributions to this field, and in fact to a lot of areas of astronomy.
And didn't that comet or asteroid catch us off guard? I mean, no one knew it was going to happen. When the Shoemaker-Levy comet slammed into Jupiter years ago, there was warning because we saw it. It was tracked by amateurs. This time, wasn't the astronomical community basically caught with its pants down?
Well, we only found out about it after the object hit Jupiter because we saw the result of the impact. We did not ever see the object that hit Jupiter, so we don't know for a fact that it was a comet or an asteroid. It was surely one or the other, but we don't know which. And so you're absolutely right. It hit Jupiter, and we saw the consequences. We certainly didn't see it in advance. But I think this provides good evidence that Jupiter is a protector of the Earth because that's one less comet or asteroid out there that might have hit the Earth.
And also, we think these objects that hit Jupiter are probably maybe less than a mile across if it's similar to the Shoemaker-Levy comet. However, the fireball which was created by the impact on Jupiter was perhaps almost the size of the Earth itself. I mean, the size of at least the Pacific Ocean. So isn't it humbling realizing that even tiny objects can create enormous destruction?
Yes, and a good example is the meteor crater in Arizona. That's something like a mile across, but it was created by an object that was not very large at all, not anywhere near a mile across, much smaller. And the reason these things produce so much damage is because they're traveling so very fast through space. So they have an enormous amount of kinetic energy. Kinetic energy is just 1/2 mv squared, where the m is the mass and the v is the velocity. And since you're squaring that velocity, anything that's traveling really, really fast, even if it's small, carries an enormous amount of kinetic energy. And that's why, a bullet, even though it's a very small thing, can kill you. And likewise, even a rather small asteroid, just 10, 20, 30 feet across, can do enormous damage and create a big crater on the Earth.
And speaking about meteors from outer space, we just finished the Perseid meteor shower. At the peak of that meteor shower, you could see perhaps 100 streaks of light in the night sky per hour, or about one every 30 seconds. Tell us a little bit about what causes a meteor shower.
Well, as these comets travel through space, some of them do cross the Earth's orbit, and they leave little bits of debris behind them, pieces of dust and ice. And when periodically every year in August, the Earth encounters a stream of debris left over by one of these comets that travels around the sun. And that's why the Perseid meteor shower occurs every August, as the Earth slams into that debris. Now, this debris is not of a harmful nature at all. These are very small objects. But because they strike the Earth's atmosphere so fast, and they burn up in a brilliant flash of light, even though they may be smaller than a grain of sand. So the Perseid meteor shower, which is just finished here in August, is one of the many meteor showers that occurs every year. Another very famous meteor shower is the Geminid meteor shower in December. That one also produces about 60 meteors per hour. Unfortunately, this year the full moon is going to be interfering with the Geminid meteor shower, so we'll have to wait for a later December than December 2009 for a good display of the Geminid.
And perhaps one of the most famous meteor showers of all time took place in 1833. That was the Leonid meteor shower, and several hundred thousand meteors could be seen per hour. There are woodcuts of that incident showing that the entire sky seemed to be full of little pieces of debris and meteors streaking across the heavens. And it was so brilliant and awe-inspiring that several religious cults can in some sense trace their lineage to the panic created by the meteor shower of 1833, which led to many doomsday cults, among them Jehovah's Witnesses and the Seventh-day Adventists. So, by the way, back in 1910, we also went through the tail of a comet. That was Halley's Comet, right? What did we learn when we went through the tail of Halley's Comet and when Halley's Comet came back 76 years after that?
Well, yes, we did actually. Halley's Comet passed so close to Earth in 1910. It was quite a spectacular sight, and we actually passed through the tail of the comet. And there were some unscrupulous people who were trying to take advantage of the public by, for example, selling comet pills to prevent any ill effects of the comet gas. Because, for example, cyanogen, which is basically cyanide, had been detected in the tail of Halley's Comet. And so there were certain doomsayers who were trying to persuade you to buy comet pills to protect yourself against Halley's Comet. Of course, when this did pass through this very tenuous tail of Halley's Comet, no ill effects were seen at all. Now, in 1986, Halley's Comet passed much farther from Earth, and it was, frankly, not a terribly spectacular sight. And unfortunately, the next time Halley's Comet comes back in 2061 will also not be a terribly spectacular appearance either, because, again, the comet is passing rather far from Earth. If we have brilliant comets between now and 2061, and I have no doubt that we will, they're going to be comets that we don't even know about right now, comets that we have not yet discovered. In the same way that Comet Hyakutake in 1996 and Comet Hale-Bopp in 1997, those were comets that we didn't know about, just a few years before they passed the Earth. So the next spectacular comet is a comet that we don't yet know about, which is kind of exciting because you never know when it's going to appear in the sky.
And speaking about the doom and gloom and mysticism surrounding these things, I think it was when Hale-Bopp sailed through the heavens last time, there was a doomsday cult, which actually saw that as a sign of the second coming when they were going to be beamed up to a flying saucer, which they thought was on that comet, and they all committed suicide. So these things really stir some very ancient, deep-seated fears in people. So let's say a few things about the future. There is an object called Apophis. Apophis, an asteroid about the size of the Rose Bowl, which is going to streak by the Earth around 2029. Any comments about an object which we know will come very close to the Earth in 2029 and then 2036?
Well, it's looking like that object is probably not going to hit us, which is good news, but it'll be fascinating to watch it sail by in those 2 years that you mentioned. I do want to mention some, we're talking about all these bad things about comets and asteroids. I do want to mention that actually, overall, asteroids and comets are actually good for us. For one thing, they built the Earth. I mean, without them, we wouldn't be here. Our planet wouldn't be here because the Earth formed by smaller objects smashing together, asteroids and comets smashing together. So without asteroids and comets, we wouldn't be here. And in some sense, you can see asteroids and comets as the leftover debris of the formation of the entire solar system. But these are the few objects that didn't get swept up by the planets or kicked out of the solar system altogether. And in addition, the asteroids and comets brought water. So the water that we need here on Earth, it came from asteroids and comets. And then 65 million years ago, one particular asteroid struck the Earth and killed off the dinosaurs, allowing more intelligent beings to evolve. I'm not sure to include all human beings in that category, but at least some human beings. And then someday we may be able to mine asteroids for iron and nickel and other metals, thereby preventing some of the environmental damage that ordinary mining does here on Earth. So overall, I would have to say asteroids and comets are, there's more good things about them than bad things. Nevertheless, it does make sense and it is prudent to discover everything out there that crosses the Earth's orbit so that we'll be able to take measures if there's something on a collision course with the Earth.
Well, one day, if we ever do see one of these things headed our way, what are we going to do about it? If you see Hollywood movies, we're all going to blow them up with hydrogen bombs. Some people say that's not a wise idea because then you have small asteroids and comets heading your way, which cause even more damage. But any thoughts about what we can do if one day there is a comet or asteroid headed our way?
Well, ideally, you'll have the longest possible warning. That's why it's essential that we discover these objects that are out there that are crossing the Earth's orbit. So, hopefully we would have 20, 30, 40, 50 years warning before something comes our way. Then we don't have to, we don't have to take such extreme measures as actually blowing the thing up. I mean, sometimes, if there's something heading your way in a very short period of time, that may actually be the best choice, to destroy the thing, blow it up, and yes, you would be left with lots of smaller things, but the hope is most of those would burn up in the atmosphere, and those that made it through wouldn't do so much damage. But ideally, we would know about these things, decades in advance, and then we can simply nudge the asteroid into a slightly different orbit. And again, if you have enough advance warning, the nudge doesn't have to be that strong in order to simply deflect the asteroid onto a different orbit that will not cause any problems for the Earth. So again, ideally, we know about these things far in advance. But if you're doing a Hollywood movie and the asteroid is discovered 40 years before it hits Earth, I mean, there's not too much drama in that, right? So that's why I think the Hollywood movies make things a little bit more dramatic than that.
Now, asteroids can be tracked using Newton's laws of gravity and telescopes, but tell us a little bit about comets from the Oort cloud, way out there beyond the solar system, whose trajectories may not be easily tracked.
Yeah, there are two comet belts in our solar system. One is the Edgeworth-Kuiper belt, which is much closer in than the Oort cloud that you mentioned. It's just beyond the orbit of Neptune. And in fact, the planet Pluto is a member of the Edgeworth-Kuiper belt. And every now and then, some of those objects, smaller objects, get perturbed into the inner solar system. And so that's the first comet belt that exists. And then the cloud that you mentioned, the Oort cloud, is much, much farther out. This is where Comet Hale-Bopp came from, and also Comet Hyakutake. These are comets on extremely long period orbits. We're talking thousands and thousands and thousands of years. Whereas, for example, in contrast, Halley's Comet goes around the sun once every 76 years. So the comets from the Oort cloud, the next comet from the Oort cloud that will be a spectacle in Earth's sky, we don't even know about because it's on such a very long orbital period that we have not yet discovered that comet.
Now, a worst-case scenario, which I don't expect to see in our lifetimes or our descendants' lifetimes, But some people say that in a worst-case scenario, you would have a soot-covered comet from the Oort cloud, unpredictable, coming from behind the sun, and because it's soot-covered, it has no tail. But after it comes back from the sun, the soot is blown off, and then it sprouts a brilliant tail, but then you have like a month to prepare for the impact. Any thoughts about a worst-case scenario and what might happen?
Well, if it were really heading straight toward the Earth, I would hope that we would devote all our resources to getting rid of it, and that probably would mean blowing it up. I mean, if you only have a month of warning, there's really not much else you can do. The more gentle, nudging an asteroid or a comet away works if you've got a decade or so. But if you've only got a month warning, then maybe what the Hollywood people suggest, maybe that would be our only choice. But to mount a mission like that would, I think, be very difficult. I mean, we just, it would be very difficult. And the question is, could NASA or maybe some other space agency be able to respond, with so little warning? I don't know.
Now, moving on, let's talk about extrasolar planets beyond our solar system. And recently, there was evidence of a backward planet, a planet that's actually spinning backwards from where it should be. So tell us a little bit about these backward planets.
Yes, all of the known planets in our solar system go around the sun in the same direction that the sun spins. However, this new planet that's been found, it's in the constellation Scorpius. It's a very strange planet. First of all, it's a giant planet. It's got half the mass of Jupiter. It goes around its star. It's very close in. Goes around its star once every 3.7 days. And it's very bloated. It's the most bloated planet that we've ever found, because even though it's only got half the mass of Jupiter, it's got 50 to 100% greater diameter than Jupiter, which means its density is incredibly low. I mean, it's got the density of balsa wood. And that's how lightweight this planet is. And as you point out, it is going around its star backward, opposite the direction that the star rotates. And these two facts, the fact that the planet is so very bloated and low density, and the fact that it's going around backward, that it's in a retrograde orbit, may be connected. The astronomers who made the discovery paint the following scenario. They hypothesized that this planet was actually born in a more normal orbit and had a more normal size, that it wasn't always so bloated. But then it had a violent encounter with another planet that flung it into a highly elliptical orbit, a backwards orbit. That explains the backwards orbit. And then as the star's gravity interacted with that planet, it made the orbit, which was originally very elliptical, more circular. And in doing so, it heated the planet and caused it to bloat up to record low densities. We've never seen a planet with such a low density as this. And by the way, the name of this planet is WASP 17b. And the WASP stands for Wide Area Survey for Planets. And again, it's in the constellation Scorpius. It's certainly one of the most interesting of the recent planet discoveries.
Now, maybe the Earth also had a collision in its past, right, that created our moon. Could you elaborate?
Yes, we do think that the Earth's moon, which is quite large for a small planet, if you look at the other, the four inner planets of our solar system, two of them don't have any moons at all, Mercury and Venus, and then Mars just has a couple small moons. Earth is unique among the four inner planets in having a big moon. And we think that moon formed when an object about the size of Mars smashed into the Earth billions of years ago, picked up debris from the Earth's mantle, cast it into space, where it conglomerated into the moon. This nicely explains the large size of the moon and also its composition, because unlike the Earth, which has a lot of iron, the moon is mostly made of rock, much like the Earth's mantle. And that would make sense, because the Earth's iron is mostly at its core, and the mantle is made of rock. And so if you have a collision that kicks up mantle debris, then you can imagine forming a satellite that's made mostly of the same material as in the Earth's mantle.
Now, also talking about collisions, our own Milky Way galaxy we think is quiet, inert, stable, but then there are also colliding galaxies. Could you elaborate on that?
Yes, there are many galaxies that orbit our galaxy, and some of these galaxies are getting torn apart by the Milky Way. For example, there was a galaxy discovered in 1994 in the constellation Sagittarius that the Milky Way is tearing apart, and ultimately the Milky Way will claim those stars for itself. And then very recently, astronomers in Japan and Australia say that the Small Magellanic Cloud, which is the second brightest of the more than 24 galaxies that orbit our own, had a violent encounter 7.5 billion years ago. In their picture, a big galaxy, a galaxy big compared to it, that was full of gas but not many stars, collided with the Small Magellanic Cloud. And this galaxy had very little iron because it has very few stars. Stars make the iron, and if a galaxy doesn't have many stars, then it doesn't have much iron. And so all of this iron-poor gas was raining down onto the Small Magellanic Cloud, and this diluted the iron abundance of the Small Magellanic Cloud shortly after that merger. And indeed, the astronomers see that after that merger occurred, the iron abundance in the Small Magellanic Cloud went down for a couple billion years.
And speaking about galactic smash-ups, the Milky Way galaxy apparently is headed for a collision with its next-door neighbor, Andromeda, two gigantic island universes which will collide 5-6 billion years in the future, who knows. But tell us a little bit about what happens when galaxies as big as ours collides with another galaxy also as big as us.
Well, it's going to be quite a spectacle. We see a beautiful example of this with the antennae galaxies in the constellation Corvus. These are two spiral galaxies similar to the Milky Way and Andromeda that are in the beginning processes of a collision. And their gravity has torn out a long tail of stars from each of the galaxies. And those galaxies will ultimately merge into one much bigger galaxy, probably a giant elliptical galaxy. Now, giant elliptical galaxies are not nearly as beautiful or photogenic as spiral galaxies. We are fortunate right now to live in a very beautiful galaxy, the Milky Way galaxy, a spiral galaxy. But if this collision with the Andromeda galaxy occurs, it will give rise to an avalanche of new star formation. The gas clouds in Andromeda will hit the gas clouds in the Milky Way and transform them into stars. So for a brief time, the galaxy will shine very brightly. But then it will likely settle down and become a giant elliptical galaxy, not nearly as beautiful as either the Milky Way or the Andromeda galaxy. So that's what will happen if this collision occurs.
Welcome. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is the second half of Exploration. In the first half of Exploration, we began a discussion with Dr. Ken Croswell, astronomer of Berkeley, talking about the perils from outer space, meteor and cometary impacts that could literally destroy the planet. And in the second half of Exploration, we're going to be talking about his latest book, The Life of Stars, talking about the life cycle of stars, how they're born, how they mature, how they will eventually die. And you know, sometimes on this planet Earth, we think we're so great. We have our wars, we have our conflicts, we have our great achievements, and yet the Earth is nothing but one tiny little dot in this much larger canvas called the universe. And today we're going to talk about the main actors in this universe, not the Earth at all, but stars. So once again, our special guest is Dr. Ken Croswell. We're talking about the life of stars. But before we begin, let me say once again that September 1st at 9 p.m., I'll be hosting a new program on the Science Channel, the second season of Sci-Fi Science, Physics of the Impossible, based on my New York Times best-selling book. Have you ever wondered, after watching some of the latest Hollywood blockbusters from science fiction, whether any of that stuff is possible? We'll find out whether or not time machines, force fields, teleportations, phasers, invasions from outer space, killer robots. Find out whether any of this is possible on my TV show, Sci-Fi Science, Physics of the Impossible, airing on September 1st at 9 p.m. Well, once again, let's get back to Dr. Ken Croswell, who will tell us that we are literally made out of stardust. Every atom of our body was originally forged in the heat of a star. Now I'd like to introduce our special guest for today. We're delighted to have with us once again astronomer Ken Croswell. This time he has a new book out called The Lives of Stars. And in fact, it's a gorgeous coffee table book, spectacular pictures from the Hubble Space Telescope showing stars in every phase of their life cycle. Since there are so many stars in the universe, by focusing our telescopes on them, you can pick up stars at every single phase of their life cycle. So once again, our special guest today is Ken Croswell. We're going to talk about the moon, we're going to talk about extrasolar planets, and we're going to talk about the lives of stars. Ken, we've heard a lot in the media about ice and water being found in the moon. And if you read all the media hype around it, you think that maybe you can get a swimming pool on the moon. But first of all, tell us how much water and ice has been found on the moon and how significant that discovery is or isn't.
Well, the significance of water on the moon is twofold. First, we have long thought of the moon as an extremely dry place. So to find any water on the moon is rather surprising. But second, there's a practical matter to all this. If we're going to send people to the moon again, it'd be really nice if there were enough water there on the moon so they don't have to drag water from the Earth and carry it all the way to the moon. Life's a lot simpler if you just live off the land of the moon. Now, 3 spacecraft, it was reported, have found evidence of some form of water on the moon. However, it's a tiny amount of water. It's not enough water for astronauts to survive on. There is, however, greater hope that there might be more substantial quantities of water at the poles of the moon, in particular the South Pole. And in fact, on Friday morning, October 9th, a spacecraft is going to smash into the South Pole of the moon, and the hope is it's going to kick up enough water and debris to prove that there really is a substantial amount of water and ice at the South Pole of the moon. And in that case, then this discovery becomes much more significant. It means that, hey, maybe if astronauts travel to the South Pole of the moon, they actually will be able to live off the land in the sense of not having to take water from the Earth to the moon to drink. Now, there's an analogy here. The planet Mercury, believe it or not, the closest planet to the sun, also seems to have water ice at its poles. So it's not completely unexpected for the moon to have ice at its poles.
Now, when we have a mental image of the moon, we have this bleak object that's baked by the sun. So how can ice possibly exist on a sun-baked moon?
Well, and the ice that exists at the poles, or that may exist at the poles of the moon, is thought to be brought there by comets that every now and then smash in to the moon. Comets contain a lot of water ice, and it's natural that that ice would then migrate to the poles of the moon. The water that has been found, the very tiny amount of water that has been found by these spacecraft elsewhere on the lunar surface, may actually arise from the solar wind. The sun gives off this stream of particles which contains a lot of hydrogen, which is not surprising since the sun is made mostly of hydrogen, and that hydrogen then reacts with the oxygen in the soil. It may surprise you, but oxygen, which we think of as being a gas, since it's what we breathe, actually makes up a substantial quantity of the ground that we stand on. The rocks beneath our feet contain a lot of oxygen, and likewise, the soil on the moon is very rich in oxygen as well. So you can imagine maybe there's some sort of chemical reaction going on between the hydrogen coming from the sun meeting that oxygen on the surface of the moon, and you have H2O, better known as water.
Now, I understand that some of this ice is found in shadows of craters and mountains, and so these areas are permanently cold. In fact, one of the coldest spots in the solar system is found on the moon, right?
That's exactly right, and that's exactly how we think that the ice survives, both on the moon and on the planet Mercury, because it's in these, as you say, permanently shadowed craters on the moon, so that the temperature never rises very high, and so the ice never sublimates and becomes gas, and so it can survive over millions of years.
Now, the media, I think, ran with this story. They said that perhaps the water can be used for rocket fuel by separating out the oxygen and hydrogen and recombining it in the engine of a rocket, and perhaps astronauts can drink it. But we're talking about minute quantities of this, right?
That's right. The discovery that was announced a week or so ago, that's absolutely right, because the amount of water spread over a vast territory. It's a tiny percentage, and I don't see it really having any practical use. If we're going to make a practical use of water on the moon, I think it's going to be coming from the ice that may be present at the South Pole. There you do have the hope that maybe there are more substantial quantities of water that astronauts could actually put to practical use. But the water that was discovered by these 3 spacecraft, no, I don't think it has any practical use. I think it's interesting that it's there because we've always thought of the moon as this really dry place. But I don't see it as having any great practical use for future astronauts.
Okay, so let's also go into outer space with the French Comets satellite. These satellites, including the United States Kepler satellite, are designed to find Earth-like twins in outer space. And there was an announcement recently about the French Comets. They found the first rocky planet in space. Any comments to make?
Well, that's a very interesting planet. It goes around its star once every 20 hours, which that should give you some idea how close that planet is to its star. In our solar system, Mercury, the innermost planet, takes 88 days to go around the sun. So you can imagine how close a planet would have to be in order to take just 20 hours, less than a day, to go around its star. It's obviously a very hostile planet, a very hot planet, not a planet you'd want to live on. And there have been some other very interesting discoveries of extrasolar planets as well. For example, astronomers discovered the first backward planet. It's a planet that orbits around its star in the opposite direction from how the star spins, which is exactly opposite the case here in our solar system. In our solar system, all the planets, and I'm even including Pluto and Eris, if you consider those 2 object planets, all of them go around the sun in the same direction that the sun spins. But this newly discovered planet goes around its star in the opposite direction from how the star spins. Furthermore, it's a really big planet, and it's a really bloated planet, and it has a very, very low density. And we actually think all of these things are connected because we think this planet was born on a normal orbit going around its star in the right direction, but then it suffered some sort of encounter with maybe another planet in that same solar system. And as a result of that, it got flipped into this backward orbit. And over time, the tide from the star that the star exerted on the planet made that orbit, which was initially quite elliptical, made it more circular. And this heated the planet immensely and puffed it up so that today it has a density that's about the same as balsa wood. It's the least dense planet ever found in space, even less dense than the planet Saturn, which, as you may know, in our solar system is the least dense planet. In fact, if you could find a big enough ocean, the planet Saturn would actually float. And this planet is even more extreme. The planet Saturn has a density 69% that of water. This planet, it's 19% the density of water, the least dense planet ever found.
Now, when we talk about the Kepler, the U.S. satellite, and Corot, the French satellite, they're able to detect planets in space which do not emit any light at all. Therefore, they're dark and they're outshined by the star by a factor of billions. So how do we detect planets that are, for the most part, invisible by telescope?
Well, there are many ways that we can detect extrasolar planets. The way that most of the planets that we know of have been discovered is through the Doppler technique, and that is a technique in which astronomers monitor very carefully the speed of a star. And if a star has a large enough planet going around it, the planet's gravity will tug the star and shift that motion of the star ever so slightly, introducing subtle red shifts and blue shifts, Doppler shifts, into the observations. And that's how 97% of the extrasolar planets that we know of have been found. In the case of the Kepler mission, though, Kepler is using a different technique. It's looking for eclipses, or transits, as we call them, as the planets pass in front of their parent stars. This causes a very slight diminution in the light that we detect from the star. And in this way, Kepler is expected to discover hundreds of Earth-sized planets going around stars somewhat similar to the Sun.
Okay, now let's go into your new book, which I understand is hitting the bookshelves right now. It's a gorgeous, well, coffee table book, I guess. It's called The Lives of Stars. And, of course, we're not talking about the lives of movie stars. We're talking about the lives of stars. So let's, first of all, start with our sun, the most familiar star of all. How was it born, and how has it evolved?
Well, the sun was born in these beautiful clouds of gas and dust that you see in the opening chapters of my book. Places like the Orion Nebula, the Horsehead Nebula, the Lagoon Nebula, beautiful clouds of glowing gas and dust in space. These clouds have newborn stars, stars where places where clumps of gas have collapsed under the weight of their own gravity. And in this way, they get warmer and then hotter because gravity heats the object up so much that it begins to glow, and a star is born. In fact, there are stars out there that actually shine through gravity rather than through nuclear reactions. These are the very young stars, stars that are called T Tauri stars. And in fact, in my book, there's an illustration of the very famous star T Tauri. That's what our own sun looked like 4.5 billion years ago. It was shining simply because it was hot. Gravity had heated it to such a high temperature that it glowed.
Okay, so we have gravity heating the gas in these nebulae, which are like nurseries for baby stars. But what makes the star ignite to become a star?
Well, as the gravity heats the core of the star, the core gets hotter and hotter, and ultimately it gets up to millions of degrees in temperature. And at that temperature, the protons in the star's center start to smash into each other. Now, as you know, protons are positively charged subatomic particles. They naturally repel each other because like charges repel. However, because of the extremely high temperature at the center of a star, the protons smash into each other, and they overcome that natural repulsion, and they smash into each other, and they engage in a nuclear reaction in which hydrogen is transformed into helium. And in fact, that's how the sun powers itself today. Nuclear reactions that are transforming hydrogen into helium. And in fact, most stars in the galaxy, most stars in the universe, use exactly the same nuclear reaction to generate their light and their heat.
Okay, so what about our sun? Our sun, I understand, is middle-aged. What does that mean? And what does it mean when our star even gets older?
Yes, the sun is indeed a middle-aged star, about 4.5 billion years old, so that's an idea of how long intelligent life has taken to arise on at least this one planet, the Earth, because the Earth was born along with the sun. And in the future, the sun is going to get it's going to get bigger and brighter. It's ultimately going to become a cool red star known as a red giant. Now, we don't have to worry about this anytime soon. We're talking many billions of years from now, but the sun will expand into a red giant. It will, at that time, emit hundreds of times more light than it does today. It will swallow the planet Mercury. It may or may not swallow the planet Venus, and it may or may not swallow the Earth. But if the Earth remains in its near present location, the intense radiation from the sun will evaporate all the oceans, and so the Earth will get fried, unless we human beings or some other intelligent species is able to move the Earth away from the sun as the sun slowly brightens over these billions of years. So the ultimate fate of the sun is to become a red giant, so one of these large, bright, cool stars that we see in the night sky.
So in other words, it's a law of physics that our sun will eventually devour the Earth in some sense, and we either have to leave or perish in the process, right?
Yes, or move the Earth away. If I calculate that if we could move the Earth into about the same orbit as Saturn, then we'll be at about the right temperature when the sun is emitting 100 times more light than it is today. That'll keep the Earth at a pleasant temperature. A red giant doesn't live all that long, and ultimately it puffs off its outer layers and forms one of these beautiful planetary nebulae, like the Ring Nebula in the constellation Lyra. And at that point, the outer layers go into space, and the inner core of the sun is revealed. And this inner core, as you might imagine, is extremely hot, but it's quite small, so it doesn't emit all that much light. And so at that point, the Earth will cool because the sun won't be giving off nearly as much light.
Now, these planetary nebula, isn't that a misnomer because they have nothing to do with planets? They are these gorgeous puffs of smoke that the Hubble Space Telescope has photographed, giving us some of the most gorgeous sights in the night sky. But the word planetary nebula, isn't that a misnomer?
It is indeed, yes. Planetary nebulae are definitely one of the most beautiful sights in the universe. I mean, if you look at the images of the planetary nebulae, they're just stunning from Hubble and from other telescopes. But the word arises actually because these objects were discovered by William Herschel. He was studying various nebulae, and he noticed that some of them looked like the disk of the planet Uranus, which is the planet that he discovered back in 1781. And he saw that, through his rather small telescope, he saw that there was a resemblance of these nebulae to the planet that he had discovered, and therefore he named them planetary nebulae. But as you correctly point out, they actually have nothing to do with planets.
Okay, so the sun will eventually die 5 billion years from now when it turns into a gigantic red giant. And then what happens when the red giant uses up much of its helium fuel? What happens then?
Well, then the red giant sheds its outer atmosphere and forms one of these planetary nebulae. The hot core is revealed, and that hot core emits ultraviolet radiation that sets the planetary nebula aglow. That's why you're able to see those beautiful objects in space. And then as that planetary nebula disperses, all that's left is that hot core, which slowly fades and cools over many billions of years. That hot core is what we call a white dwarf, which is an object that has roughly the same mass as the sun, but only the size of the Earth. So in this transformation, a red giant goes from being one of the largest and brightest stars in the galaxy to being one of the smallest and faintest, going from a red giant to a white dwarf. So it's an amazing metamorphosis.
Now, the white dwarf star is a dwarf star. So first of all, how big is it? And if it has the mass, roughly, of a star, how dense is it?
It's incredibly dense. A spoonful of a white dwarf would weigh tons, because as you point out, these are still stars, and they're still quite massive. The average white dwarf has a mass about 60% that of the sun, but they're a little bigger than the Earth. And so, if density is simply mass divided by volume. And because these objects have substantial mass but a very small volume, they're incredibly dense. And in fact, the light that leaves a white dwarf actually gets redshifted as it tries to struggle away from the white dwarf because the gravity on the surface of the white dwarf is so very intense.
And finally, what happens to the white dwarf? Does it die with a bang or die with a whimper?
It definitely goes out with a whimper. It simply cools and fades because it's no longer using any of its fuel. It's no longer engaging in nuclear reactions. It's simply living on, it's sort of resting on its laurels, you might say. The reason it's hot is simply because for billions of years in the past, it has generated heat and light through its nuclear reactions, but as a white dwarf, it no longer engages in those nuclear reactions. So as it emits light into space, it loses energy, it cools off, and it therefore fades. And its ultimate fate is to become what we call a black dwarf, which is a white dwarf that has basically faded and cooled to near invisibility.
So isn't it true that everything we see around us, the trees, the air, the bones of our body, everything will eventually wind up as a piece of nuclear waste in a black dwarf star?
Well, in the sense that the Earth will continue to orbit the sun, and the sun will ultimately become a white dwarf and then a black dwarf, I guess you could say that too, yes. Yes, indeed.
Okay, so the sun goes out with a whimper. Now let's talk about big stars. I mean, really big stars, 20, maybe 50 times bigger than our sun. I understand their life history is a little bit different. They're on the fast track.
Oh, they're very much on the fast track. They are spendthrifts. They were born with much more mass than the sun, more than 8 times the mass of the sun. Now, these stars are actually quite rare, but they're very brilliant, so they're very easy to see in the night skies. For example, Orion, brilliant constellation, has lots of high-mass stars, Rigel and Betelgeuse being 2 of the most famous. And these stars do not go out with a whimper at all. They live fast and they die young. Now, you might think that a star that's born with more mass should live longer than a star like the sun. And, logically that sounds true because to a star, mass is fuel. But these stars burn their fuel so much faster than the sun that they often die just a few million years after their birth. And when they use up their fuel, they go out with a bang. They explode as supernovae, dramatic supernova explosions that can outshine the light of an entire galaxy. And in fact, we see many remnants of these supernovae. The most famous is in the constellation Taurus, where our ancestors saw a star explode in the year 1054. The site of that explosion is now marked by an expanding nebula called the Crab Nebula. It marks the place where a massive star, exploded as a supernova about 1,000 years ago.
Okay, and if you look dead center in the heart of the Crab Nebula, you find the corpse of this star. What do you see?
You see a pulsar. And in fact, if you look on page 43 of my book, you will actually see that pulsar. It's arrowed with a yellow arrow. So you can see that at the very center of that Crab Nebula, you can see the pulsar at the center of the Crab Nebula. That pulsar represents what used to be the core of that very massive star. And now, keep in mind, this star, before it exploded, was one of the most immense stars in the entire galaxy, one of the most luminous, one of the brightest. It's now, that Crab pulsar, it's now just 10 miles across. So the size of basically of a city. So it's gone from being, this incredibly huge thing to being this incredibly small thing. And the pulsar consists mostly of neutrons because the protons and the electrons have been smashed together to form neutrons, which are electrically neutral. And these, we were talking earlier about how dense white dwarf stars are. Well, neutron stars are even more dense. A spoonful weighs more than 1 billion tons. And if you were to drop a pebble from a height of 4 feet above a neutron star, above a pulsar, the gravity is so strong that it would pull down that pebble and cause it to crash into the surface at 5 million miles per hour.
So I guess a teaspoon of neutron star material would probably outweigh a mountain range, right?
Oh, yes, yes, I would think so. Yes, indeed.
Okay, now, some people say that even this core of neutrons, which is 5, 10, 20 miles across, even that could be unstable if it's really big, and it could collapse once again. What happens then?
Well, if a star is so big that it just can't hold itself up even after collapsing into a neutron star, it becomes the ultimate collapsed object in the universe, a black hole. This is an object that is so dense and has such immense gravity, nothing can escape its grasp, not even light, which is the fastest thing in the universe. Black holes are extraordinary objects. There are probably millions of them scattered throughout our galaxy, although the very biggest black hole in the Milky Way is at the very center of the Milky Way in the constellation Sagittarius. That black hole weighs about 4 million times more than the sun does.
So tell us a little bit about that black hole. I mean, the center of galaxies. Don't we see monster black holes at the center of galaxies, including our own, as you mentioned?
Yes, indeed. Most large galaxies are thought to have massive black holes at their centers. And when I say a massive black hole, I'm talking about something that's millions or even billions of times more massive than the sun. Our black hole, the black hole at the center of the Milky Way, is actually fairly modest as these black holes go. It's, as I say, about 4 million times the mass of the sun. The nice thing about it is that because we're just 27,000 light years away from it, we're able to study it better than we can the black holes of other galaxies. But some of the black holes in other galaxies are absolutely immense. For example, there's this galaxy, this elliptical galaxy in the constellation Virgo called M87, and it has a black hole that's 6 billion, that's with a B, times more massive than the sun. So even though the black hole at the center of the Milky Way is big and certainly the biggest black hole in our galaxy,